Today we're going to be talking about the structure and properties of organic molecules. And the atoms in organic molecules are held together by bonds. So we're going to talk first about the types of bonding we can have. Then we'll look at the shapes of the organic molecules and the physical properties that result from those shapes. Atomic orbitals are the spaces, the regions of electron density where you can find electrons about particular atoms. And for the carbon atom, we know we have an s orbital available for bonding, and we have 3 p orbitals that are available for bonding. The s orbital is a spherically shaped orbital, and the p orbitals have this dumbbell shape, and we have 3 of them. One can be aligned along the x-axis, we call it the px orbital. One can be along the y-axis, and one can be drawn along the z-axis here. And they're typically shaded different colors because that's representing the sign of the wave function. The sign changes at the center there and at the origin, and that's why we typically show them in different colors. But that's the general shape of these atomic orbitals. So atomic orbitals are defined as regions with a high probability of finding the electron density. These are defined by mathematical equations that are called wave functions. And I already mentioned that the sign changes at the node, but the other thing to mention is at the node where we have a change of sign, the probability of finding any electron density at this point has a 0 probability. Now, if we want atoms to come together to form molecules, the electrons can no longer reside in atomic orbitals. They must be shared between atoms in new orbitals called molecular orbitals. The way molecular orbitals are formed is we take 2 atomic orbitals and overlap them and form new orbitals. What we'll find is if we take 2 atomic orbitals, they will combine to give 2 new molecular orbitals. And the reason we get these 2 results is because there are 2 possible combinations of those mathematical equations. So let's take a look at an example. For example, the simplest molecule we have, just H2. Let's imagine taking a hydrogen atom and another hydrogen atom, each of them with a single electron, and bringing them together to form a bond. We typically represent a covalent bond as a line drawn between the 2 hydrogens. We call this a sigma bond. And what this line represents is it represents 2 electrons that are shared in a molecular orbital called a sigma molecular orbital. And that's what we refer to as a sigma bond. Now, each of these hydrogens is coming in with an s orbital. And so here we have the s orbital coming from one hydrogen, s orbital coming from a second hydrogen. Let's imagine that mathematically those have the same sign. What are the 2 possible ways that they can combine? Well, they can combine in a positive way. If we add these 2, we would describe that as being in phase, and the result would be a molecular orbital that has a kind of a shape like this. That's what we call a bonding molecular orbital, the sigma bonding molecular orbital. And this is what it looks like when you have favorable overlap between the 2 atomic orbitals. Okay, but another way they can come together, if you can imagine the s from hydrogen A subtracted from the s orbital of hydrogen B, we would describe those now as being out of phase, and they would no longer have a favorable overlap. They would be held apart like this, and we call this molecular orbital an anti-bonding molecular orbital, and we label it as sigma star. So a sigma with an asterisk there, we read that as sigma star. And what we have here now is a node where the sign has changed from one sign to the other, and so that's going to be a higher energy orbital. And this is a phenomenon that's true in general, that as you increase the number of nodes in your molecular orbital, or even in your atomic orbital, you're going to increase in energy. It's going to be less stable the more nodes that you have. Another way to represent this combination of atomic orbitals to give molecular orbitals is with an orbital diagram like this. We can show one hydrogen coming in with its atomic orbital. The s orbital had a single electron in it. On the other side, we have a second atomic orbital with 1 electron in it as well. And when they combine and they form a bond to bring those 2 hydrogens together, we will now have 2 electrons in the system, and they will have 2 new possible places to reside. We have a sigma orbital, and we have a sigma star molecular orbital. And where will those two electrons want to go? Well, as usual, we're going to fill the orbitals starting with the lowest possible energy. So we'll pair them up and we'll put them in the lowest energy sigma molecular orbital, and that's kind of a graphical representation of what a sigma bond looks like. So what if we wanted to form a pi bond? Pi bonds come about by overlapping p orbitals. And so now again, let's have the same idea. We bring in a p orbital from one atom and a p orbital on a second atom. Because we have two atomic orbitals, we're going to get, as a result, two new molecular orbitals because of these two possible combinations. If the signs are matching at the top and bottom when we bring them together, that's where we're going to get our favorable constructive overlap, and we're going to get kind of a region of electron density up here, a region of electron density below. This is our bonding molecular orbital. We call this a pi bond, or a pi MO. And that's what the electron density looks like in a pi bond. You have no electrons in the area where you would find the sigma bond between the two nuclei. Instead, you have a cloud of electrons above and below the sigma bond. Okay, how can these p orbitals, what's another way that they can combine? If you imagine flipping one of them over as if you were subtracting the two, you would now have a poor, you would have a mismatch in all directions. And so this is what we call the pi star molecular orbital. You can see here that there is a node in this direction and a node in that direction. So this now is a very high energy orbital. We can look at it analogous to the way we saw the formation of the sigma bond. We can imagine the p orbital coming in with a single electron from one atom, a second p orbital with a single electron from the other atom, and when we combine these two, we have two new molecular orbitals that have been formed, one of a lower energy, that is the pi molecular orbital, one of a higher energy, we call that the pi star molecular orbital, and we're going to locate these two electrons in the lowest energy orbital possible. We're going to pair them up and put them in the pi molecular orbital. Now overall, when we take a look at the possible orbitals then in which electrons can reside in a molecule, if we want to look at them overall, if we list them in the order of increasing energy, we'll find that the most stable place for electrons to be is in the sigma bond, in a sigma molecular orbital. These are going to be their most stable electrons, lowest energy electrons. That makes them pretty stable, pretty unreactive. These are great bonds to form and going to be more difficult bonds to break. These are lower in energy than a pi bond. Remember, a pi bond has that node, and so it's going to be higher in energy. And if you have a lone pair of electrons, we call those non-bonded electrons. Those are in an n-type orbital, and that's a higher energy level still from pi bonds. So these two types of electrons, non-bonded electrons and pi electrons, because they're a little higher in energy, these are a little less stable than the sigma electrons. They're going to be more reactive. We're going to see lots and lots of chemical reactions involving the breaking of pi bonds or involving non-bonding electrons in reactions. Okay, and just like the sigma bond is the lowest energy, sigma molecular orbital is the lowest energy, that sigma star then is the highest in energy, and the pi and the pi star have this relationship. Of course, the anti-bonding orbitals are always going to be the highest in energy, and they're much, much less stable, and they're usually empty. We in a normal bonding situation, we will not put any electrons in those pi star or sigma star orbitals. So you might think, why is it relevant to even know about those? Why should we even consider those? What relevance do they have? And let me just very briefly give some justification for that. And that is under the topic of electronic transitions. So if we imagine a ground state molecule, a stable molecule, and we have a pi bond in that molecule, we know we're going to have two electrons in that pi bond. They're going to be paired up. They're going to be in the pi molecular orbital. The pi star molecular orbital is empty. But if you were to introduce some light energy, especially ultraviolet light, the molecule can absorb some of that energy if the energy amount is exactly equal to this energy gap between the pi and the pi star, then the molecule can absorb a photon of light and promote one of these electrons up to a higher energy level. So the pi star offers a place for the excited electrons to go. So this is what an excited state might look like, an excited pi bond that's absorbed some light. Now, when this gets very interesting is that the energy gap here between the pi and the pi star will shrink, will become smaller if the pi bond in question is conjugated with other pi bonds. And to be conjugated means you have an alternating pi bond system. Pi bond, sigma bond, pi bond, sigma bond, and so on, such as this system. We have a pi bond here, and then we have a pi bond right next door and another pi bond right next door. And what happens is, because there's a p orbital on each of these pi bonds, there's one pi bond, and then here's another pi bond. If you think about those p orbitals involved, we get this long system of pi bonds that are all overlapping and related to one another. And it ends up shrinking this gap. And this gap can become so small that instead of requiring ultraviolet light to be absorbed by the molecule, you could move into a lower energy light, such as visible light. So as we increase the number of conjugated pi bonds, so as the system gets longer and more extensive, you will increase the amount of resonance stabilization. That's this interaction between adjacent p orbitals. And that's going to decrease the energy needed for this transition from pi to pi star. And if visible light is what's being absorbed, then the molecule in question is going to appear to us as being a colored molecule. So when you look at the structure of things like beta-carotene or chlorophyll, you're going to see this extended pi network, and it's all because of the existence of those pi star molecular orbitals that the absorption of light is made possible. Let's talk now about the case of hybrid orbitals, because it's not always so simple as having s orbitals and p orbitals overlapping to form sigma and pi bonds. If you consider carbon, we know that carbon's atomic orbitals has 4 valence electrons. The outermost orbitals, atomic orbitals for carbon, are the s and the 3p orbitals. And so if we were to fill in those 4 electrons, we would pair 2 of them up in the lowest energy s orbital, and then we would move up to the p orbital, and we would spread those out as such. This is what our stable electronic configuration looks like with carbon. But we know that carbon likes to have 4 bonds, and the way it looks right now, you would think that maybe just because it has these 2 single electrons that might be available for bonding, it can only have 2 bonds. Well, it's easy enough to promote some energy, add some energy into the system, and promote an electron so that, in fact, we can have a carbon with 4 unshared electrons already for bonding. Okay, so that leads us toward a carbon that carbon can now have 4 bonds. Experimentally, however, we observe that a molecule such as methane, CH4, has 4 identical CH bonds. Now, how can that be? If this is our atomic orbital picture, you would imagine that a bond formed by overlap with a spherical s orbital would be quite different than a bond formed by overlapping any of these p orbitals. So how is it that we come up with 4 identical bonds? Well, the answer to this mystery is that the atomic orbitals in carbon undergo hybridization. This is the mixing of atomic orbitals to give new orbitals that we call hybrid orbitals. And what would it look like if you took an s orbital, a spherical s orbital, and mixed it with a dumbbell-shaped p orbital? Well, you would get something that's still dumbbell-shaped, but it's elongated on one of the sides. So it's more spherical and not symmetrical. And we're still going to have a node here. We're still going to have the sign change. So it looks something like this. And that's what our hybrid orbitals are going to look like. Now, it turns out there's a variety of different hybridizations that carbon can undergo. And we'll see that the type of hybridization that carbon undergoes depends on the number of groups around the carbon. And we're going to call these groups regions of electron density. So we'll look at some examples and we see how we can determine the hybridization that's required. So right here we have 3 different sample carbon molecules, and each of these carbons has quite a different bonding situation. Now if you look closely, you'll see each carbon has 4 bonds, like carbon typically does. A stable carbon is going to have 4 bonds, but the electrons are arranged in different ways. So for each of these, let's look at them one at a time and see if we can what observations we can make. Now for this molecule, even though there are 2 carbons, let's just consider one of the 2 carbons when we're describing the hybridization. This carbon has 1, 2, 3, 4 separate sigma bonds, so we're going to describe it as having 4 separate regions of electron density. Such carbons are said to undergo a hybridization called sp3, or you could say that this carbon is sp3 hybridized. It's called sp3 hybridization because you mix the carbon's s orbital with all 3 p orbitals, and so the result is called sp3. The result then, because we've mixed 4 atomic orbitals, we're now going to get 4 new molecular orbitals, 4 new hybrid orbitals, and we're going to call these sp3 hybrid orbitals. So this carbon no longer has ordinary s and p orbitals. Instead, it has 4 orbitals around it that are all sp3 hybrid orbitals. Now, what kind of geometry are we going to get as a result? Here we can use VSEPR, valence shell electron pair repulsion theory. If you have 4 groups of electrons and you want to spread them out as far as possible, you're going to have a tetrahedral geometry, meaning we have about a 109.5 bond angle in a molecule such as this. How about the next molecule? Again, let's look at just one of these 2 carbons and ask about its hybridization. Again, this carbon still has 4 bonds, but if you look now, it's arranged into just 3 groups. We have a single bond here, and a single bond here, and a double bond in this region. So this carbon has only 3 regions of electron density. And such a carbon is described as being sp2 hybridized, and the reason we give it that name is because this carbon mixed one of the s orbitals with only 2 of the p orbitals to form its new hybrid orbitals. That means one of the p orbitals on that carbon is still there as an unhybridized pure atomic orbital with the dumbbell shape. And we'll see that in just a bit. So what's the result of this hybridization? Well, we took 3 atomic orbitals and mixed them, so we're now going to get 3 new hybrid orbitals. So we're going to get 3 new hybrid orbitals. What are they called? They're called sp2 hybrid orbitals. Plus, this carbon has the unhybridized p orbital, so it has 1 p orbital. So every carbon that is sp2 hybridized will have around it 3 sp2 hybrid orbitals and 1 p orbital. And what kind of geometry do you expect when we have 3 groups of electrons that we're trying to get apart from each other as far as possible? How about if we spread them out in the corners of a triangle? That would be the best. We call that trigonal planar. Trigonal planar, meaning it's going to be a flat molecule, a flat carbon with bond angles about 120 degrees, like in the corners of a triangle. Okay, and our last example here has a carbon with 4 bonds, but these 4 bonds now only have 2 regions of electron density, a single bond in one direction, triple bond in the other direction. And if we have only 2 regions of electron density to accommodate, you might be seeing a trend here, and you might predict that the hybridization is going to be called sp hybridized. And it's called that because what we need to mix is the s orbital along with just 1 p orbital, which leaves the other 2 p orbitals there unhybridized. And as a result, when we've mixed 2 atomic orbitals, we get 2 new hybrid orbitals. So we're going to have 2 sp hybrid orbitals. And what else will this carbon have? It will still have these 2 p orbitals plus 2 p orbitals. And what about an atom that has just 2 groups of electron density that you want to get as far apart from each other as possible? VSEPR shows us that we're going to try and get them just in a linear direction. 180 degrees from each other would be as far apart as you can possibly get. Okay, so these are the basic geometries that we're going to be looking for, sp3, sp2, and sp. Let's look at some examples on how we can apply this. So here's an example. What if I asked you to assign the hybridization of the following molecule? And what's given here is just a backbone, so we can just get a little practice drawing Lewis structures. And then if we needed to assign the hybridization, here's what we have to do. First, we have to make sure that the Lewis structure is complete, including lone pairs of electrons. Okay, and then hybridization is something that doesn't describe a molecule, it describes an atom. So hybridization is going to be for each atom. In other words, what is the hybridization of this nitrogen, this carbon, all 3 carbons, and this oxygen? Those each have a hybridization that we can describe. Hydrogens can't undergo hybridization because all they have is a single s atomic orbital, so there's nothing to hybridize, so there's nothing to mix. So the hydrogens always bring an s, but all the others can undergo hybridization. And then what we're going to do is we're going to count the regions of electron density to see how many need to be accommodated. And what is a region? That's going to be either a lone pair of electrons, or a single bond, or a double bond, or a triple bond. Each of those counts as one region. Okay, so let's do that. First, let's complete the Lewis structure. If we want to, we can probably do this by inspection. This carbon needs 4 bonds, so we can make that a double bond. Oxygen likes to have 2 bonds and 2 lone pairs, so we can add 2 lone pairs there. That satisfies both of those atoms. And if we put a triple bond from this carbon, now this carbon has the 4 bonds that it likes, and the nitrogen, in order to be neutral, has 3 bonds and 1 lone pair, so that looks like we've completed the Lewis structure quite nicely. Okay, so what is the hybridization for each atom? Well, we could start with this carbon. What we're going to do is we're going to count the regions of electron density. We have 1, 2, 3, 4 sigma bonds, so we must have 4 regions of electron density. Our hybridization in that case is sp3. How about the next carbon over? We have 1, 2, 3 regions of electron density around here. So 3 regions. 3 regions is not sp3. 3 regions is sp2. And remember, the reason it's called sp2 is we mixed the s plus the 2 p's. So the way we got these 3 hybrid orbitals is by mixing 1 s and 2 p's. And that's where you're going to see the regions of electron density matching the number of atomic orbitals that went into this. So just a little hint you can have is thinking about adding the exponents. Okay, how about this carbon? Here's the triple bond and the double bond and the single bond. That counts as 2 regions. So that's going to make him sp hybridized. The nitrogen has a lone pair and a triple bond, so this nitrogen also has 2 regions, so this is also sp hybridized. And then finally we look at this oxygen. The question would be, do you think we should count these lone pairs together as one region or separate? And it comes down to whether or not you think they want to be very close together or they want to be far apart. And of course, lone pairs are going to repel each other, so we count each lone pair separately. 1, 2, 3 regions of electron density. That's going to be sp2 hybridization. So this is how you're going to assign the hybridization for the atoms in a given structure. Now let's see what these molecules are going to look like in 3 dimensions. If we wanted to sketch particular atoms or molecules, how do we take that hybridization and translate it to a sketch and some Lewis structures? So first let's take a look at the atomic orbitals. sp3 we said was tetrahedral. So the way we usually draw a tetrahedron is we draw 2 bonds in the plane. So we'll draw those as straight lines about 109.5. Well, none of us really knows how to draw exactly 109.5, but we know what 90 degrees looks like. We know what 90 looks like. We know what 180 looks like. So 109.5 is somewhere between. So just a little wider than 90 is usually what looks good. Okay, and to draw a tetrahedron then, the other two bonds, the other two hybrid orbitals, are going to be out in this direction. We're going to draw one as a wedge, and we're going to draw one as a dash, and that is showing some three-dimensionality. The wedged bond is drawn as a wedge because it's projecting out toward you, projecting up from the page. And the dashed bond is dashed because it's actually hidden from view. It's behind the page. So anytime you see something dashed, it's going to be pointing away from you and in the background. Okay, sp2 had 1, 2, 3 regions of electron density. So this is our trigonal planar. So we can draw those in the plane. And our bond angle is 120 here. Again, 120 looks very much like 109.5. Just a little wider than 90 degrees. Okay, but what else did any atom that is sp2 hybridized had not only these sp2 hybrid orbitals, actually let's label these. So it has 3 orbitals, each called an sp2. In fact, we can label these up here. These were our 4 sp3 hybrid orbitals. And in addition to these hybrid orbitals, remember an sp2 hybridized atom also has a p orbital that was not hybridized. And that p orbital is going to be perpendicular to the plane of the sp2 hybrid orbitals. So remember, it's a dumbbell-shaped orbital. So what we could do is maybe we can draw one half of it kind of as a wedge sticking out at us, and the other half as a dash sticking below the plane, because it's really, if this is the plane of the sp2, it's projecting straight out toward you and straight back. So what we do is we tilt it just a little bit so we can see both parts. Okay, or what we can do is we can draw the p orbital very nicely. Okay, so this is a p orbital. And in fact, this is our other p orbital. Both of these parts was from the p orbital. We could draw the p orbital in the plane. But if we do that, that tips the rest of the molecules. So now that my sp2 plane is on its edge, one bond or one orbital can be in the plane and the other two become a dash and a wedge. So either of these would be acceptable drawings for an sp2 hybridized atom. Depends on what your focus is, whether you really want to see the p orbital or you really want to see the bonds. A lot of times we like to draw the bonds in the plane, so the p orbitals get shifted as dashes and wedges like that. Okay, and finally, an sp hybridized atom has 2 sp hybrid orbitals that are 180 degrees from each other, linear. And let's draw this nice and big so we have some room to work with. So this is 180 degrees. And what else does an sp hybridized atom have? It also has 2 p orbitals on this, if this is a carbon, let's say. And so we could draw one of those p orbitals in the plane perpendicular to the sp line. And then the second p orbital is going to be perpendicular to that still, orthogonal. We could draw one as a wedge and one as a dash. So here is one p orbital, top and bottom. Remember, p orbital always has 2 parts. And the second p orbital, back and front. Without getting too messy, sp hybridized atoms usually get a little messy. There's a lot going on. So make sure you give yourself plenty of room when you're drawing these so you don't have to fit too much stuck in there. And this is, I didn't even see there. And remember, we had the p orbitals were aligned along the x, y, and z axes. So whichever p orbital, in this case, it's the x, px, as drawn, that was hybridized. And so the other 2 p orbitals are the ones that are still there, the one along the y-axis, the one along the z-axis. So what is it going to look like when we bring these hybridized atoms together to be a molecule, and how can we draw those 3D sketches? Well, if you ever need to do a 3D sketch, the very first thing you want to do is determine the hybridization of the carbons involved, or any atoms involved, because it's the hybridization that's going to determine the geometry. So let's take a look at this first carbon and count the regions of electron density. There's 1, 2, 3 bonds to hydrogen, and then a 4th bond to carbon. 4 regions of electron density means we have an sp3 hybridized carbon, and this second carbon has the exact same arrangement with 3 bonds to hydrogen, 1 bond to carbon. So if we wanted to draw a sketch, we would start with either one of the carbons. Let's do the carbon on the left and draw it tetrahedrally. That's a little bit of an angle. If we draw it tetrahedrally so that we have about a 109.5 bond angle, we have it attached to a carbon and a hydrogen. And where are the other two bonds? Well, to be tetrahedral, we're pointing off in this direction. One is a wedge, one is a dash. And that's what a tetrahedral carbon is going to look like. Then we come to the next carbon. He needs to be tetrahedral as well. We've already drawn one of the bonds in the plane. The second bond to be drawn in the plane can be either up here, 109.5, or down here, 109.5. And those would both be okay. Let's draw it up in this direction. Okay, but if we draw this bond up here, then the dash and the wedge are down in this direction. Okay, and if we take a quick look at a model here, this molecule is called ethane, and ethane then has two tetrahedral carbons. These are both CH3s. These lines that lead that end at nothing, we just assume are hydrogens. And so what we have is the carbon-carbon bond is drawn in the plane. We have two CH bonds that are also drawn in the plane, and then each of them has a hydrogen that's projecting out toward you. We draw as a wedge. These two hydrogens are pointing away from you. We draw those as a dash. So this is what our ethane molecule looks like. Okay, but notice that there's more than one 3D sketch we can have for this molecule because we can rotate around this bond. There's free rotation around this sigma bond, and so we would actually have some additional 3D sketches we can draw. So for example, because we can rotate around here, we can have, let's just say we can have the structure where the first carbon stays the same, but the second carbon has the other hydrogen that's in the plane pointing down here. If this is where you draw the two bonds that are in the plane, then the ones that are out and back are pointing up here. So really working with models and really helps you understand what a tetrahedral atom looks like, and it's going to be much, much easier to draw the 3D sketches to make them more realistic. But the goal of your 3D sketch is that it actually has the same shape as what you're seeing. Okay, how about a carbon that has a double bond? This carbon has 1, 2, 3 regions of electron density. So this is an example of an sp2 hybridized carbon. And again, this symmetrical molecule has two sp2 hybridized carbons. So to sketch that, we draw a trigonal planar arrangement for the 3 sigma bonds. Hydrogen, hydrogen, carbon are the 3 bonds we have there. And on the second carbon, we also have a trigonal planar that's going to share the same plane as the first one. So all these are about 120-degree bond angles. Okay, and those are all the sigma bonds, all being planar. And now we have to show what this pi bond looks like. How do we get a pi bond? Well, that's by overlapping a set of 2 p orbitals. And remember, every sp2 hybridized atom has a p orbital. It's right here. We can kind of draw it as a wedge and a dash on the first carbon, and then a wedge and a dash on the second carbon. And then one way or another, we want to show some kind of interaction between the top half and the bottom half to represent a pi bond. Remember, the pi molecular orbital had a cloud of electron density above the sigma bond and a cloud of electron density below, so this 3D sketch represents that pretty reasonably. And this is a model of this molecule. This molecule is called ethene, and you can see that if we draw it, one way to draw it is just completely to put all 6 atoms in the plane of the board, and then the p orbitals are going to be right here, perpendicular on the first carbon, and the second carbon, here's our p orbitals, they're going to be overlapping above and below the plane. So we're going to draw that as sticking out and sticking back. Okay, another possibility, though, is to draw this with the p orbital and the pi bond illustrated very cleanly. So p orbital on one, p orbital on the other, connection of the two above and below. So that's a nice looking pi bond. But if our pi bond is what we're showing in the plane of the board, what does that do to our sigma bonds, to our hybrid orbitals? Well, now we've tilted the molecule like this, so you can see now that these 2 hydrogens are projecting out towards you. We need to draw those as wedges, and 2 of them are as dashes. Okay, now if you're reviewing this molecule perfectly straight on, these are going to be hiding each other. So what we do is we tilt the molecule just a little bit so that the back hydrogens are up a little, or we could tilt it this way so they're down a little. Those are both okay. But we need to show, let's show the two wedges coming a little bit in a downward direction, but really they're projecting straight out towards you. And then the two hydrogens slightly up, and they're back. So both of those are good ways to draw the trigonal planar sp2 hybridized atoms. And this molecule of ethene. Finally, we could take a look at this last molecule. We have an example here of an sp hybridized, two sp hybridized carbons that are attached. We have, it's sp because we have just a triple bond and a single bond, so just two regions of electron density. And so if it's sp, that means we have 180 degrees linear bonds, linear sigma bonds going straight out 180 degrees in either direction. And now we need to represent two sets of pi bonds, which are really two sets of p orbitals. So we're going to draw that. One of them can be in the plane perpendicular to the sp. There's one pi bond. And where is the second pi bond going to be? That's going to arise from the pz orbital on one carbon, front and back, overlapping with the pz orbital, front and back on the second carbon. And again, without making a huge mess, we can maybe show the interaction of this top and back. And what we have actually is actually like a cylindrical type of a structure with this. Here's a model of this acetylene unit. This molecule is called acetylene. This one piece represents the carbon-carbon triple bond. Here's it one carbon and the other carbon, and we have the two pi bonds here. So really what we end up with is actually a cloud of electrons just completely surrounding this linear arrangement. And then we have an sp hybrid orbital sticking out directly in one direction and one in the opposite direction. So let's look at another example of doing a 3D sketch. Like we said, we need to complete our structure and then assign a hybridization. And then when we do a sketch, we might have a molecule with several different rotations and possible drawings. And so it's a good idea to try and draw the maximum number of atoms possible in the plane of the page. That's going to be the simplest drawing you can have. So here's an example. And I see some things that are missing from my Lewis structure. I know that this oxygen needs some lone pairs. Okay, I know that this must be a triple bond here between the carbon and the nitrogen, and then this nitrogen must have a lone pair. This is actually the molecule we had on the previous slide where we assigned the hybridization. So you'll remember our hybridization for the nitrogen and the carbon were both sp. The carbon and the oxygen were both sp2. And this CH3 out here is sp3. So as we get a more complex molecule, we need to bring the geometries about each of the atoms together in a cohesive way. So what we can do is we can start with this middle carbon, kind of right in the middle. This carbon we know is sp2, so it's trigonal planar. He has a carbon and an oxygen for the 3 sigma bonds for the sp2 hybrid orbitals. And finally, he has a pi bond up to oxygen. So we're going to represent that since we chose to draw these in the plane. The p orbital is going to be sticking out and back. And on oxygen, we have the same thing, a p orbital sticking out and back, and then some kind of overlap here. Some instructors like to show 2 electrons here to represent the 2 electrons being shared in the as the pi bond, and everyone has their different style. Okay, what else does this oxygen have? Well, he has the lone pairs, and where are those lone pairs oriented? Because this is sp2 hybridized, and we've already shown the p orbital coming out and back from that. The lone pairs are in sp2 hybrid orbitals that are in the plane. One way to draw that is to just draw it as a straight line, just showing geometry. It's not a sigma bond, but that's one way that you can draw it. Or another way to draw it is just to draw kind of a lobe, a hybrid lobe that's in the plane, and put the lone pair in there. We'll see that. We'll handle the nitrogen that way. Okay, now let's come to this carbon. This carbon we said is sp3 hybridized, so that means tetrahedral. We've already drawn one bond at this angle, so where does the second bond go? Well, it needs to be 109.5. We can choose to go up here. We could choose to go down here. Either one is fine. But if this is where our two bonds are that are in the plane, the other two bonds are down here. One is a wedge, one is a dash. Doesn't matter which is which, because this is another example where we're tilting the molecule just slightly. When we have a tetrahedral atom, if these are the two bonds we're drawing in the plane, then the wedge and the dash are really totally aligned with each other. So we tilt it a little bit to the left or right. Doesn't matter which way you draw the wedge. And we have hydrogens in these positions. Okay, and then finally we come to this carbon. He's sp hybridized, okay, and here's where we really need to be careful with our geometry, because we know sp hybridized means linear, and we've already shown the first bond in this direction, so the second bond has to continue in that same direction. Right? This is the bond angle that needs to be 180 degrees. So be careful from thinking that linear always means horizontal on a page. Linear means it's 180 degrees going in either direction. And this nitrogen then is also sp hybridized, and so the lone pair is also linear. And so let me show you, instead of drawing a straight line like this, we could draw the hybrid orbital pointing off in this direction to indicate that that's where you would find the electron density that's non-bonded electrons. And then finally, we want to show our p orbitals. Now, where do the p orbitals go? Because the 180 degrees is right here, the linear. That means the p orbital needs to be perpendicular to that. So see how the molecule gets all tilted to its side? We connect the top and the bottom. And then the second pi bond comes from the p orbital out and back. So it all starts from recognizing what the hybrid orbitals look like, and then bit by bit we can bring them together as molecules, and as simple molecules and more complex molecules. But ultimately, our goal is that the drawing that you have, and it's like this, sorry, the drawing that you have should very closely match the structure that you have. So here we have our linear CN triple bond, and see how it's kind of pointed off in this direction. Our CO double bond is pointing straight up, and our CH3 is over here. We chose to draw it. Let's tilt this a little bit. We chose to draw it with the hydrogen pointing in the plane, and then here's our dash and our wedge hydrogen. So really an accurate 3D sketch should very much look like the shape of the molecule in reality. Let's try one more example. This one's a little trickier. This molecule is known as allene, and it's kind of a classic molecule to study 3D sketches for. When you draw out allene, you see that it has carbon-carbon double bond, two carbon-carbon double bonds that are directly connected to one another. The CH2s on the end are sp2 hybridized. Pretty straightforward, because they have three regions of electron density, two hydrogens and the double bond. And this middle carbon has a double bond here and a double bond here, so this is sp hybridized. But what's interesting about this is usually our sp hybridized atoms usually are triple bonds, and so what's different is we have double bonds here. So let's see what that sketch would look like. We could start with that middle carbon. We know he's sp hybridized, so the sigma bonds are going to be linear, 180 degrees from each other. So this will overall be a linear molecule with respect to the carbons. Then we could draw one of the pi bonds. Let's draw the pi bond to the left. That's a p orbital here and a p orbital here. And we show the pi bond. And then we can finish off this carbon. We've already shown the pi bond. If the pi bond is up here, what does that do to our two hydrogens? These two hydrogens can no longer be in the plane because they have to be perpendicular or orthogonal to that p orbital. So the hydrogens are out and back. How do we arrange this second pi bond? The second pi bond has to come from the other p orbital that is on this carbon. Remember, every sp hybridized carbon has 2 p orbitals. So the second p orbital is out and back. There must be an aligned p orbital on the last carbon here, and that's how we form our second pi bond. So one pi bond is going to be above and below the molecule. The other pi bond electrons are going to be in front and behind the molecule. Now what does that do to this carbon? Where do the hydrogens go here? Because we've shown the p orbital coming out and back and front and behind the plane, that means the sp2 hybrid orbitals are in the plane. And so what we get for this molecule of allene is a very interesting structure because it has a twisted structure where the carbons on the left, the hydrogens on the left are pointing out and back, a wedge and a dash. We have a linear carbon in the middle, and the hydrogens on the right, are going to be in the plane, up and down. Okay? Here's one set of p orbitals, and then here's the second set of p orbitals, like this. And let's talk about hybridization and how it relates to resonance. Because a lot of times when we draw a Lewis structure, there may be more than one possible Lewis structure that we can draw. We call this resonance. When there's more than one structure we can draw, more than one arrangement of electrons, and we know we have this resonance because we have an allylic lone pair, and a lone pair that's next to a pi bond, so that lone pair can be shared and the pi bond can move up, and we can get this new resonance form. Okay, the question that we have here is, what is the hybridization? What does that mean for the hybridization and the geometry of this nitrogen? Well, you might think that, well, it has 2 hydrogens and a lone pair and a single bond. That's 4 regions of electron density. So ordinarily you might expect that nitrogen to be sp3 hybridized. But when you look at the second resonance form, we see that it has just 3 regions of electron density, the hydrogen and the double bond. So this nitrogen is clearly sp2. We also know that in in resonance, that electrons are the only things that move and not the atoms or the sigma bonds. So in fact, this nitrogen can't be sp3 in one resonance form and sp2 in another. In reality, it's sp2 the entire time. So this is the one exception where the exercise of simply counting the regions of electron density can be a little tricky, because if you have a lone pair of electrons that can be involved in resonance, specifically an allylic lone pair of electrons, those electrons must be in a p orbital in order to have resonance delocalization. So let's take a look at what this resonance picture really looks like. If we consider the geometry of this molecule and the resonance hybrid, we know that middle carbon is sp2 hybridized. I'm sorry, this is nitrogen. The middle carbon is trigonal planar sp2 hybridized. But the nitrogen is also sp2 hybridized, and the oxygen is sp2 hybridized. And what we have is a p orbital on the oxygen, a p orbital on the carbon, and a p orbital on the nitrogen. And those 3 p orbitals are aligned, and that is what's sharing the electrons. That's what resonance picture looks like. You have a partial bond. Sometimes it's drawn as a dashed partial pi bond here, because the CN relationship has a partial double bond character, and the CO bond has a partial double bond character. So we could draw it like this. So this is what the actual hybrid looks like, and this is what resonance always has, is electrons that are involved in p orbitals. So this lone pair must be in a p orbital, which means it can't be sp3 hybridized. That has no p orbitals. It needs sp2 hybridization, so one of the p orbitals is free, and that lone pair then can interact with the other p orbitals from the carbon-oxygen double bond. Okay, so because we're not able to move our atoms, it can't be tetrahedral in one case and then trigonal planar in the other, because the atoms are fixed throughout resonance. It's always going to be sp2 hybridized. We can't have sp3 on any atom that is undergoing resonance. So now let's talk about physical properties that we might expect for organic molecules and perhaps how they relate to their 3D structure as well. Physical properties are things like water solubility, boiling points, that sort of thing, melting points. And all of these properties are based on intermolecular forces, forces between molecules. So for example, if we take a look at a sample of methane that is a liquid, if we heat that and we heat it until it reaches its boiling point, these molecules are going to gain enough energy to be separated from one another. So each of these methane molecules, CH4, will now no longer have the close contact that they did in the liquid stage. They will be freely flowing and independent in the gas phase. And this is what the phenomenon of boiling looks like. Okay, notice, just a quick point, notice that my methane molecule has stayed intact during the boiling process. We're not breaking up the carbons and the hydrogens. We're not having hydrogens and carbons breaking up. So we're never breaking our sigma bonds, our pi bonds, our intermolecular bonds. But what we do need to do is we need to disrupt the intermolecular attractions between the methane molecules. Okay? If those CH4 molecules are strongly attracted to each other, if there's a very strong attraction to one another, what will that do to the boiling point? It's going to be more difficult to pull those molecules apart from one another, so we're going to have to put more energy in to do that, meaning increase the temperature even more. That's going to increase the boiling point if we have a strong attraction between molecules. So what are the types of interactions? We call these non-bonding interactions between molecules. What are the types that we can have? Well, there's three that we'll be discussing. One is called dipole-dipole, and this is the kind of interaction that we get when we have polar molecules. Another type of non-bonding interaction that's actually quite strong is called hydrogen bonding. That's when we have either an OH or an NH as part of our molecular structure. And the last one is called van der Waals forces or London forces, and this is what we look for, especially when we're dealing with non-polar molecules. Okay, so let's look at each of the three of these and see what effect they can have on the physical properties of molecules. A dipole-dipole attraction is what we have when we have two polar molecules near each other. A polar molecule could be represented like this, where we have two poles. We have a part of the molecule that is electron rich, electron deficient, or partially positive, and a part that is electron rich, that is partially negative. And you can imagine that if we had two such molecules, they are going to be aligned in such a way that the electron deficient region is going to be attracted to the electron rich region, and so on. And so when we have a polar molecule, there is quite a strong attraction between polar molecules, just like you would imagine the attraction that two magnets have each other because they each have poles. So let's look at a series of compounds here. Okay, how about the boiling points of sodium chloride? This has a boiling point of 1,413 degrees C. This next molecule has a boiling point of 76, and this last one has a boiling point of 36. So let's see if we can use the concept of dipole-dipole interaction to explain this. Okay, first of all, we have sodium chloride. This is actually not even a polar molecule. We know this is an ionic molecule, and that can kind of be described as the most extreme dipole you have when something is so polar that it's actually ionic. And so we call this attraction not a dipole-dipole, but we call this an ion-ion interaction. And the sodium cations are so strongly attracted to the chloride anions that you have to put in a huge amount of energy in order to melt this, to boil this is the boiling point. So even to melt it is very difficult. And then if you want to put it in the gaseous phase, these separate ions, it's going to take incredible heat. And if you've ever tried to salt something that you still have in the frying pan, when you might notice that when the salt crystals land on the hot frying pan, they stay totally solid, and it would be very difficult to heat those to melting. And how about these two? We have a 76-degree boiling point here and a 36-degree boiling point. How can we explain the difference there? Well, because of the presence of this carbon-oxygen bond, oxygen is much more electronegative than carbon, so it pulls electron density toward itself. That makes this a polar bond, and this becomes then a polar molecule. And this last molecule, this line drawing, just represents a carbon chain. So we have carbon-hydrogen bonds and carbon-carbon bonds. All of those bonds are nonpolar. So as a whole, this is a nonpolar molecule. And that's why it has such a low boiling point. So the overall trend here is that as you increase polarity, you increase your boiling point. And one last thing to note is when we talk about the idea of having a polar molecule, remember you need to not only look for polar bonds, but you also need to consider the geometry of the molecule. So for example, if we have carbon tetrachloride is a tetrahedral molecule. Well, how do I know it's tetrahedral? Because this carbon has 4 chlorines around it. That makes it sp3 hybridized. So this is where our hybridization is going to pay off. We'll be able to understand the geometry of the molecule. And even though carbon-chlorine bonds are polar, we have these polar. We have these dipole. We have these polar bonds pointing in equal and opposite directions. So we have no net dipole. So as a whole, this is a nonpolar molecule. So in making the decision on molecular polarity, we need to consider not only the polar bonds, but also the geometry of the molecule. Of course, this, since it has no polar bonds, the geometry of the molecule is irrelevant because there could be no net dipole moment here. Okay, how about hydrogen bonding? This is really another example of a dipole-dipole. It's just an extremely strong one. And that's when you have a hydrogen on any of the 3 most electronegative atoms in the periodic table. So an NH bond is going to be an extremely polar bond in the direction of the nitrogen, which puts a lot of partial positive character on the hydrogen, partial minus character on the nitrogen. And oxygen is even more electronegative, so that is an even stronger dipole. And of course, HF has this as well, but HF is, its own molecule. It can't be a part of a larger molecule. So that's not as relevant when we're looking at the boiling points and physical properties of organic molecules. So for example, let's take a look at this series of compounds. We have water. We have a carbon chain with an OH. We have a carbon chain with an oxygen in the middle, and then we have a carbon chain with no oxygens. Okay, so right off the bat, we can see that we have another example of something that is completely nonpolar down here. And so that's why we have such a low boiling point, minus 42 degrees C. And if we compare these 2 molecules, they're isomers of each other. They both have 2 carbons and an oxygen. So we expect them to be polar molecules, but because this one has an OH bond, that means it can hydrogen bond. Can form hydrogen bonds. In other words, one molecule of ethanol is very strongly attracted to another molecule of ethanol, and so it's going to be more difficult to to separate them. Okay, this molecule has an oxygen, but there's no hydrogen directly attached to that oxygen. So it cannot hydrogen bond. And look at this huge difference in boiling points, about 100-degree difference because of the lack of that hydrogen bonding. So really, really strong effect here. You might also think, well, is this also nonpolar? Do these dipole moments cancel? You know, this is a polar bond and this is a polar bond, but do they cancel each other? And would we describe this also as a nonpolar molecule? Well, what do we expect for the hybridization of that oxygen in the middle? We know that oxygen has 2 lone pairs and 2 bonds, so this is actually going to be sp3 hybridized. Rather than calling it tetrahedral now, we call it a bent molecule, because really all we look in geometry is the location of the atoms. And so in this bent molecule, this polar bond is pointing up and to the right. This polar bond is pointing up and to the left. So the left and right components do cancel, but they both have this upward component that with nothing to cancel. So this is actually a polar molecule. So that explains why this molecule with the oxygen has a higher boiling point than the molecule with all just carbons and hydrogens. There's our increase in polarity. Okay, and look at hydrogen. We know with water. We know water has a boiling point of 100 degrees. Okay, why is it such a huge boiling point, very high boiling point for such a small molecule? Because it has 2 OH bonds. So this has lots of hydrogen bonding going on with water. And so it has an extremely high boiling point there. And by having an OH, 2 OH bonds, one way we could describe water as being a hydrogen bond acceptor, because it has an oxygen that can participate in hydrogen bonding, and it is a hydrogen bond donor. So you'll hear those words when a hydrogen bond is being described, and water participates in both directions. And what you can show is that we have this water molecule, because these bonds are so polar. There's a very large delta minus, partial minus charge on this oxygen, very significant partial positive on these hydrogens. So what is the interaction going to be between water molecules? We're going to have a very strong attraction between the partial plus hydrogen of one and the partial minus, oxygen of the other. Okay, and it's so strong that we actually draw this dotted line here to represent a hydrogen bond. And so this water molecule can donate a hydrogen bond to another water molecule. It could also use its oxygen to form a hydrogen bond with another water molecule. And so, as you can imagine, we just get this huge network of oxygen of water interacting with other water molecules. Huge interaction between the water molecules that really accounts for a lot of the physical properties that we have for water. The fact that it has such a high surface tension, has such a high boiling point. It's a very ordered structure. Water really likes interacting with other molecules of water because of this hydrogen bonding. So hydrogen bonding is one of the most important things to look for when you're considering physical properties such as boiling point, because it's such a huge, you can see from these numbers, there's a really significant rise in boiling points when you can have hydrogen bonding. Okay, and finally, let's consider nonpolar molecules. If what we're trying to do is disrupt intermolecular attractions when we're, let's say, boiling a molecule, a sample, whatever could possibly keep nonpolar molecules together? Why aren't they all just gases all the time? Well, we have something known as van der Waals forces or London forces, and these are temporary dipoles that can occur in nonpolar molecules. So let's take a look at a nonpolar molecule, just represent it here, and let's imagine that just at some point there might be an uneven distribution at the surface. So an uneven distribution of electrons at the surface. They're not perfectly evenly distributed. Maybe we have a slight excess of electron density here, or a slight reduction there. Well, when that happens, then if it sees another molecule, it's going to induce the opposite dipole, temporary dipole, in the neighboring molecule, and we're going to get an attraction there. Okay, so what we get as a result of this is we get a temporary attraction. Gives a temporary attraction. Okay, and the key is this is happening at the surface. So what's observed is that the greater the surface area a molecule has, the greater the van der Waals attractions it's going to have. And one observation then is, all other things being equal, as you increase your molecular weight, you're going to increase the boiling point. Increase your molecular weight, you're going to increase the boiling point because you will simply have more surface area that can interact. So again, let's take a look at a series of compounds here. These are all hydrocarbons, meaning they contain nothing other than carbon or hydrogen. And so these are all nonpolar molecules. We see that this one has 4 carbons, 1, 2, 3, 4. And the one on this end has 5, 1, 2, 3, 4, 5. And so simply having more carbons, higher molecular weight, means it's going to have a higher boiling point. Okay, but let's take a look at this middle structure. This is interesting because this is also a 5-carbon structure and also nonpolar, but we see a pretty significant difference in boiling point here. How can that be explained? And what we have in this case is we have this first molecule is kind of is an example of a straight chain structure, more linear, and this second molecule is an example of a more branched, more highly branched. And the more branched a molecule becomes, it becomes more spherical. This is actually quite a spherically shaped molecule. And then if you imagine how straight chain molecules will interact with one another, we see that they can have a lot of interaction because they have a larger surface area. So this has more surface area, and therefore we're going to have more van der Waals. What is that going to do to the boiling point? It's going to increase the boiling point. Okay, but a branched molecule, if it's a spherical molecule, imagine throwing those together, they have very little surface area, less contact, and that's why it has a lower boiling point. It's easier to take these molecules apart. A lot of times for van der Waals forces, I kind of like to think of them like Velcro strips, the hook loop fasteners. If you have a long Velcro strip that's tied together, it's going to be really hard to pull those apart because there's so much contact surface area. But if you have something like the little dart game where it's a ping pong ball that has some Velcro on it, you know it's very hard to make those stick and very easy to take them apart. That's because it has such a smaller amount of surface area. So if you imagine nonpolar molecules as being kind of sticky, then the more surface area you have, then the higher boiling point you're going to have. Now, one thing to mention, I'm not going to talk much about boiling points, okay? I'm sorry, melting points. This less contact is something that's going to affect the boiling point as shown, but we can make a note here that if a molecule is highly spherical, it will have better packing of the crystals when it's a solid. So in the solid state, if you have something that's spherical, you can pack them very tightly, and what happens as a result, it's going to be difficult to disrupt that crystalline structure, and you will see an increase in melting point. So melting point is a little more complex than boiling because in addition to just the attraction between molecules, you also have the issue of how well packed, how tightly packed the molecules can fit to one another. Besides boiling point, another physical property we can take a look at is water solubility. The key to looking at solubility is that like dissolves like. So in order to be soluble in a solvent, a solute should have the same characteristics as that solvent. So when we consider water, we know that water is polar. Water can hydrogen bond, so it's really going to like molecules that can do the same, and they're going to have good water solubility. So again, let's look at a series of compounds here. We've listed these kind of in decreasing order of water solubility. This first one is the most soluble in water. In fact, we describe this as being miscible with water. Miscible means that it's soluble in all proportions. So this is ethanol. You can never add too much ethanol to water and have it separate out as a separate layer. It will continuously dissolve in water. Okay, but looking at this next structure, when you have 3 carbons, it is now less soluble. In fact, you can only dissolve 8 grams of this structure in 100 milliliters of water. As soon as you try and add more than 8 grams, it's going to separate out. In fact, because this is a liquid, it's going to separate out as a second layer. So it has some water solubility, but a limited amount. And in this compound now, when we have 1, 2, 3, 4, 5, 6 carbons, we see that this is the least soluble of all of them. Less than a gram of this material will dissolve. Very, very little will dissolve in a 100 milliliter sample. And what we have here is, as we're increasing the number of carbons, increasing the length of this carbon chain, what sort of characteristics do we associate with a carbon chain? Well, this is something that is nonpolar. So as you increase your nonpolar component, nonpolar part of the molecule, you lower your water solubility. It's going to be nonpolar. You could even describe this as being hydrophobic, because water is so polar that something that is nonpolar will not like water at all. And you could even call it greasy. Things that are have very long carbon chains are things that are going to seem greasy to us, and something that won't want to dissolve in water. And so, so here you can see that as you increase your polarity, you increase your solubility. Of course, the examples I've shown all have OH groups, which means they can also hydrogen bond with water. So even though this has a very long carbon chain, it's at least slightly soluble, because this OH group is extremely hydrophilic, really likes water because it's not only so polar, but it can interact with water and hydrogen bond with it. Okay, and finally, let's take a look at one more example. This molecule is called acetone, and this is also miscible with water. You may have worked with acetone before in the lab. It's a commonly used solvent, especially for cleaning glassware. Nail polish remover is usually acetone based, and that's an aqueous solution, so it's a fairly common organic solvent. And it too is miscible with water, so it's completely soluble in water. Okay, why is it so well dissolved with water? Well, one thing is that it's polar, and it's not only polar because we have a dipole moment with a carbon-oxygen bond, and oxygen being more electronegative than carbon, but also because this carbonyl, this CO double bond, can have resonance. So that means there's two ways to draw acetone. And so this second resonance form is also contributing to the actual structure of acetone. And this resonance form actually has a plus and minus charge. So has some ionic character there. So this carbonyl carbon, this carbon here has a very highly partial positive character. The oxygen has a highly partial negative character. So again, this is an extremely polar molecule. That's what makes it so much like water, even though it's an organic molecule. Okay? And in addition, it can also be a hydrogen bond acceptor. Acetone itself cannot hydrogen bond with other molecules of acetone because it has no OH group. So acetone is a fairly low boiling solvent. Again, if you ever got some acetone on your skin with nail polish remover, it feels cold, evaporates very quickly. It's quite low boiling. Okay, but because it has an oxygen with lone pairs, it can participate in hydrogen bonding with one of these partially positive hydrogens in water, and so we still can form hydrogen bonds because it's a hydrogen bond acceptor. So water solubility is another physical property that we can explain in terms of polarity and perhaps molecular geometry sometimes too. And one other thing we can look at with organic molecules is the fact that we can have isomers of a given structure. An isomer, two isomers are compounds that are related because they have the same molecular formula. So in other words, they have the same number of carbons, hydrogens, nitrogens, oxygens, and so on, but they're different compounds. Okay, and traditionally the definition of isomer, the initial one that most of us learn in general chemistry, are known as constitutional isomers or structural isomers. And these are isomers that have different connectivity. So you have the same atoms, but they're put together in a different order. So for example, here we have a 4-carbon chain and a 4-carbon chain, but here the double bond is in the first 2 carbons, and here it's between the middle 2 carbons. These are 2 different compounds, but they are but they are isomers of one another. Okay, and they can have quite different connectivity. Here we have 4 carbons and an oxygen, so we can maybe have it with an OH group, or we can have an oxygen, sandwiched between carbons, or that OH group can be on a different part of the carbon chain, and so on. There are several other isomers that we can draw, but what relates them is they are all have the formula C4H10O, which relates them as isomers. And one last example here. Both of these structures look quite different, but they both have 5 carbons and 6 hydrogens and 1 oxygen. So isomers can be very, very different compounds of one another as long as they have the same formula. Now there's another kind of isomerism called stereoisomers, and that's something we're going to be getting into quite a bit in organic chemistry. And this is where you have molecules with the same formula and the same connectivity, okay, but they have different spatial arrangements. So only by looking at their 3-dimensional shape can you tell that they are different molecules. So for example, both of these molecules have 1, 2, 3, 4, 5 carbons, and they have a double bond between the second and the third carbon. 1, 2, 3, 4, 5 carbons, double bond between the second and third carbon. So these molecules will actually have the same connectivity, same order of atoms, and even the same name when we learn about naming, but these are not interconvertible. These are 2 different structures. Remember, you can't rotate around a carbon-carbon double bond. So these are unique compounds, but the only way you know they're unique is when you look at their shape in space. Here, the 2 carbon groups are on the same side of the double bond. We describe that as being the cis stereoisomer. And here, the carbon groups are on opposite sides of the double bond. We call those trans isomers. So this is just one brief example into the idea of having stereoisomers. Again, more to come later. Sometimes this is called cis-trans isomerism. It's one type of stereoisomerism that you can have. And finally, as an overview and preparation for the material to come, let's take a look at the idea of having functional groups. And this is where we have an arrangement of atoms put together in a common way. And much throughout organic chemistry, we usually study it by going from one functional group to the next. And for each functional group, we'll learn that molecules that have this particular arrangement of atoms very often have the same reactivity, the same behavior, and so we study those classes of compounds one at a time. So the simplest type of carbon compound we can have is just called an alkane. An alkane, like methane, is when we have nothing more than carbons and hydrogens and nothing else. No double bonds, no other atoms. We could abbreviate it just as an R group with a hydrogen. We use the letter R to represent any kind of carbon chain. So you'll see the letter R a lot to represent just a generic carbon chain. And so, for example, we have this molecule, it's called methane. For each of these functional groups, not only will we be studying their behavior and their reactivity, but we'll also be studying their nomenclature. How do we name these compounds? Another group that we'll study early on are called alkyl halides. That's when you have an alkane with a halogen now attached. And so this, for example, is R with a chlorine on it, or because the halogens are often denoted just with the letter X, we could use the abbreviation RX to represent any sort of a wide variety of alkyl halides. And we'll learn the nomenclature for that as well. This would be called chloromethane because it's a methane with a chlorine attached to it. Aromatic compounds are interesting compounds that have this characteristic 6-membered ring with 3 alternating pi bonds. Those compounds are called aromatic. This specific compound is called benzene. And so, again, at some point throughout the course of organic chemistry, you're going to learn about what it means to be an aromatic compound and what compounds other than benzene itself could be described as aromatic. And the abbreviation AR represents some aromatic group like this benzene 6-membered ring. If you were to have a double bond, a carbon-carbon double bond in a structure, we call those compounds alkenes. And if you have a triple bond, we call those alkynes. When we study the reactions of carbon-carbon pi bonds, we usually kind of look at alkenes and alkynes closely together because they have very similar reactivity. And an alcohol is what we call it when we have an OH group attached to a carbon chain. So ROH represents a variety of alcohols, such as methanol. This is when you have methane and you put an OH, we now call it methanol. And this is kind of an example of the many suffixes we'll see in our nomenclature. Depending on how the name of the compound ends, it tells you what sort of functional group. So every time we see an OL, it tells us that somewhere in the structure we have an OH group. And an ether is what we call it when there's an oxygen, but it's not attached to a hydrogen, it just has a carbon on either side. So this is called an ether when you have ROR. There's a wide variety of functional groups that contain the CO double bond. The CO double bond is called the carbonyl. This is a hugely important functional group in organic chemistry, and as you can see, it's ubiquitous all throughout organic chemistry and organic molecules and natural products and naturally occurring compounds. Depending on what two groups are on each side of the carbonyl, we can break these compounds up into different classes of functional groups. So the simplest ones are when we have just carbons on either side, or maybe a carbon and a hydrogen. When there's a hydrogen, we call it an aldehyde. And when there are two carbons on either side, we call it a ketone. So again, ketones and aldehydes, we'll look at their reactions and nomenclature and all that hand in hand. If you have an OH and a carbonyl on the same carbon, this is no longer an alcohol. This entire functional group is now, the entire set of atoms is taken together as a single functional group. These are called carboxylic acids, and they would be abbreviated RCO2H. If you expand RCO2H, one of these oxygens has to be a carbonyl, double bond, and then the other is an OH. So acetic acid is an example of a carboxylic acid. That's this particular structure right here. And then these last groups, this last set of compounds are called carboxylic acid derivatives. So these are compounds that are derived from carboxylic acid. So these are typically studied kind of hand in hand in the same time, generally around the same time. So if you have a halogen, we call it an acyl halide, or maybe an acid chloride, for example, if it's a chlorine. If you have an OR group here, it's no longer an ether. When there's a carbonyl in an OR, we call that an ester. Notice how similar these names are. So a lot of this nomenclature really comes to being very familiar with subtle differences in names. When there's a nitrogen, we call that an amide. When we have an oxygen surrounded by carbonyls, we call that an anhydride. And when we have a CN triple bond in a structure, we call that a nitrile. All of those are carboxylic acid derivatives. And like I said, this is just a preview of what's to come, because bit by bit we'll be learning about the nomenclature of each of these functional groups, and then the reactivity and their general behavior and physical properties. So thank you for joining us.